class 20, chain rule and inverse functions. First, make a little note to yourself. You might want to bring your textbook to our next class. We're going to learn a few new derivatives in this section and a general formula for differentiating the inverse of a function. And I'm going to start with the derivative of the natural log function. And at the risk of giving away the punchline, here's the punchline. The derivative of ln x is 1 over x. So that means that the derivative of the ln of some stuff would be what? 1 over stuff, yeah, times the derivative of the stuff. Okay, so let's just practice using this a little bit. So if I want to take the ln of x cubed minus 7x, that is the ln of some stuff. So the derivative would be 1 over my stuff times the derivative of the stuff, which would be 3x squared minus 7. And I could simplify that. I just multiply those two fractions. Okay, so for b, I have the ln of 3x to the 9th. So this is a double chain rule. My innermost function is 3x to the 9th. Then I'm taking the ln of that, and I'm taking the ln of that. Right, so this is a 3-function composition. I have to use the chain rule twice. What is my outermost function? Ln of some stuff, right? So this will be my stuff. And I'm taking the ln of that stuff. So my derivative is going to be 1 over it. 1 over the ln of 3x to the 9th. Okay, but then I have to take the derivative of this stuff, right? The inside function. And the derivative of the ln of 3x to the 9th is 1 over 3x to the 9th. But that was the ln of some stuff, so I have to multiply by the derivative of that stuff, which is 27x to the 8th. So then I can simplify a bit here. 3 goes into 3 once, and it goes into 27 9 times, and those 8 x's can cancel with 8 on the bottom there. And when I simplify, I'm going to get 9 in my numerator over x times the ln of 3x to the 9th. Does that make sense? Let's do that same one using the Leibniz notation. Because I know that I haven't finished grading your quizzes yet, but I was looking them over, and the double chain rule definitely trips some people up. And if it happens to trip you up, turn to the Leibniz notation. Let it walk you through the whole problem. So the ln of 3x to the 9th. Okay, so we have 3 functions here. My innermost function will be, we'll call it u, right? So u is going to be 3x to the 9th. And then work your way out, then I have the ln of u, right? And that's going to be some other function, maybe we'll call it w. W will be the ln of u, and u is 3x to the 9th. And then I finally have my outermost function, which we'll call y. Y equals the ln of w. So if you work your way backwards, right, replace w with an ln u, then replace u with a 3x to the 9th, then these two equations say the same thing. So I've just broken this down into the 3 functions that are being composed to get my original. All right, so if I want to find dy dx, right, I want to find the derivative of y with respect to x, I can write this as a chain. Okay, well that would be dy dw times dw du times du dx. So this is a chain where where things cancel, right? My dw's cancel, my du's cancel, and I just end up with dy over dx. All right, so now I just have to take each of these derivatives. dy dw, the derivative of ln w would be 1 over w. That's what dw du is. That's w prime. So that's why this works in Leibniz notation. Yeah. dw du is 1 over u. And then du dx is 27x to the 8th. And then you go back and make your substitution, right? W is really the ln of 3x to the 9th. U is really 3x to the 9th. Then I have 27x to the 8th. So this is exactly what I got when I was just thinking about take the derivative of the outside, evaluate it at the inside, multiplied by the derivative of the inside. This is exactly what I got. But I just can use Leibniz notation to make it like more formal, you know, to have something to fall back on when I lose intuition. So this simplifies the same to 9 over x ln 3x to the 9th. All right, one more example with using derivative of ln. I want the derivative of the ln of x to the 7th. What do you think? Yep. 7 times the ln of x to the 6th, because this is some stuff to a power. So I'm applying the power rule to the stuff, but then you still have to multiply by the derivative of the stuff, which is 1 over x. Okay, so I'm just going to look at a quick graph of ln x and 1 over x and make sure that it makes sense graphically that 1 over x would be the derivative of ln x, because we haven't proven it. So let's at least get some graphical evidence. Okay, so first I'm going to graph y equals ln x. So there's my graph of the natural log function. Not a bad window. And then I'm going to graph 1 over x. But before I do, let's think about the derivative of ln x. So way down here, like when I'm close to 0, if I were to draw tangent lines along here, what do they look like? Yeah, they look like nearly vertical lines. Yeah. So which means that the slope would be close to infinity. Yeah. They're nearly vertical lines, but they actually have a slightly positive tilt. So they are close to infinity. And then here, right along here, when it starts to curve a little bit, the slopes get less and less steep, right? And they're getting less and less steep and less and less steep and less and less steep, but they never go negative, right? So it looks like they're getting closer to 0. So if I graph 1 over x, ignore this part. If you graph 1 over x, does that have that quality? Are they close to infinity, near 0, and close to 0 as we go to infinity? Yeah, so that makes sense. Okay, so the beauty of starting with an equation, just some statement we know is true, is that when you have an equation, you can do anything you want to both sides of it. Pretty much, you can do anything you want as long as you do it to both sides. So I am going to take d dx of both sides. I'm going to take the derivative of both sides of this equation. So I take the derivative of both sides. The derivative of the right side is easy. What would that be? 1. Okay. And then the right side, this is a composition, right? So I'm going to have to do the chain rule. So this is the sine of some stuff. What is the derivative of the sine of some stuff? Cosine of that stuff. Cosine of the inverse sine of x times the derivative of the stuff, right? But that's what I don't know. I don't know what the derivative of inverse sine is. So I'm just going to write it as d dx of the inverse sine of x. All right, so now I could solve for d dx of the inverse sine. Could divide both sides by that cosine of the inverse sine. So I'm going to isolate d dx of inverse sine of x because that's what I would like to know. Okay, running out of room, so those cancel. And I have that the derivative of the inverse sine is 1 over the cosine of the inverse sine. Okay, but I can do a little bit better. I can simplify that a little bit. When you take the cosine of something, right, that something is an angle, right, in the unit circle. Whatever you take the cosine or the sine or any trig function of, that thing is an angle. That's how the cosine is defined. So I am going to say, let the inverse sine of x be some angle theta. We're just going to rename it as theta. So if I draw a picture of a right triangle, and this is theta. All right, how does this go? Got it. All right, so remember that the sine of the inverse sine of x is x, right? So that means that the sine of theta is x, right? Because I called inverse sine of x theta. All right, so I go to my triangle. Here's theta. The sine of theta is x, which is opposite over hypotenuse. So let's let this be x and this be 1. Opposite over hypotenuse. So sine theta is x. And then I can use the Pythagorean theorem to get the third side. So the third side would be the square root of 1 minus x squared. Just do this thing squared plus x squared has to give you 1 squared. Solve for the missing side. So take this one step further. This now says 1 over cosine theta, right, instead of inverse sine of x. But what is the cosine of theta in this triangle? That's the tangent of theta. Yeah. Yeah, the square root of 1 minus x squared over 1, adjacent over hypotenuse. So this is going to be 1 over the square root of 1 minus x squared over 1, but I won't bother writing it. So this is the derivative of the inverse sine of x. So coming up with that formula is a little bit tricky, but let's just write down what we learned here. The derivative of inverse sine is 1 over the square root of 1 minus x squared, which means if I want to take d dx of the inverse sine of some stuff, right, instead of an x, I'm going to have some stuff, so that would be 1 over the square root of 1 minus my stuff squared times the derivative of the stuff. So that is a general thing we can do. This is a general approach we can use when you want to find the derivative of an inverse function. If you know the derivative of the function itself and you want to know the derivative of its inverse, you can write down a true statement composing the function its inverse will give you x, take the derivative of both sides, and solve for the derivative of the inverse. In this one, we had to be a little tricky once we had solved for it, then we had to be a little bit tricky in the simplifying with the triangle and stuff. So we can do a similar technique. Did I skip anything? I don't think so. Okay. So I can use a similar technique to find the derivative of arctan, inverse tan, and the derivative of inverse cosine. Okay, so I will leave you to play with coming up with this formula on your own. But the inverse tangent derivative is 1 over 1 plus x squared. And that means that the derivative of the inverse tangent of some stuff would be 1 over 1 plus stuff squared times d dx of the stuff. All right, let's take a time out from proving things to use the formulas we've proven. Okay, I want to find the derivative of the arcsine of 5x over the arctan of x cubed. And if you're not familiar, arctan or arcsine, those are just like synonyms for inverse tan and inverse sine. Okay, so why don't you try this one on your own or in your groups. All right, so let's discuss together. This is the derivative of a quotient, so I'm going to have to apply the quotient rule. So the derivative, remember, is the denominator. So always start with the denominator. So that is going to be the arctan of x cubed times the derivative of the numerator. So the derivative of the inverse sine of some stuff is going to be 1 over the square root of 1 minus the stuff squared, and the stuff is 5x, so this is going to be 25x squared, or 5x in parentheses squared. Okay, so that is the derivative of the inverse sine of 5x, the derivative of the inverse sine of some stuff, but then I have to multiply by the derivative of this stuff, which would be what? 5. So there's the denominator times the derivative of my numerator minus the numerator times the derivative of the denominator. Well, the derivative of arctan of some stuff is 1 over 1 plus the stuff squared. So this is going to be 1 over 1 plus x cubed when you, that is my stuff. So when I square x cubed, what do I get? X to the 6th. So that's 1 over 1 plus my stuff squared times the derivative of the stuff. What's the derivative of x cubed? 3x squared. All over the denominator squared. Whew. I don't want to simplify that. I don't think I will. Nothing obvious is jumping out at me. Did anybody simplify it at all? Yes, I could put 5 over the square root, and I could put 3x squared over 1 plus x to the 6th. I think I'm just going to leave it.
Is it also valid for
Oh, yeah. 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 So this technique that we use to find the derivative of inverse sine can be used to find the derivative of any inverse function by differentiating both sides of the equation f of f inverse equals x. Okay, so before I do that, let's go to a separate page here. And I gave away a punchline at the beginning that the derivative of ln x was 1 over x. Let's derive that. Okay. So that's going to be my f inverse, right? F inverse of x is ln x. What is f of x then? E to the x. So I could write a true statement by composing those two functions, and I should get x back, right? So I have e to the ln of x should give me x. Compose two inverse functions, you get the x back. All right, so then I use my special trick, and I take the derivative of both sides, d dx of e to the ln x equals d dx of x. Right side's easy. D dx of x is 1. The derivative of e to some stuff would be e to the stuff times stuff prime, right? E to the stuff, e to the ln of x times the derivative of the stuff, which is ln x. And then what is e to the ln of x? X. So this says that x times the derivative of ln x equals 1. Divide both sides by x, and we get d dx of ln x is 1 over x. Pretty neat, huh? So we can do this in general. For any function f and its inverse, you can write a true equation, f composed with f inverse of x gives you x back, and take the derivative of both sides, and let's see what we get. Right? If I want to find the derivative of f inverse, so I'm just going to apply that same technique. F of f inverse equals x. Take d dx of both sides. Okay. So right side's easy. D dx of x is 1. And the derivative of a composition, right, is the derivative of the outside, right? So my outside function is f. So this is going to be f prime. So usually we have a formula when we're trying to evaluate the derivative of composition. But in this case, I don't have a formula, so the best I can do is if I want the derivative of f, I can just write f prime. Okay. So the derivative of the outside evaluated at the inside, which is f inverse, times the derivative of the inside, which is d dx of f inverse. And that's what we want. I want to know what is the derivative of f inverse. So I divide both sides by f prime of f inverse. And we get d dx of f inverse of x is 1 divided by f prime evaluated at f inverse of x. In general, if you know a function f's derivative, you could use this formula to get its derivative, the derivative of f inverse. But, I mean, why bother memorizing formulas when we have this cool little technique here? You could just do this, right? So you could plug into this formula if you're a formula person, or you could take the function, its inverse, compose them, take the derivative of both sides, and solve for the derivative you're looking for, like we did with ln and inverse sine. But let's see, we can write this down. This is 1 over f prime evaluated at f inverse. All right, so I know the derivative of f inverse evaluated at 3. Oh no, sorry, that's what I'm trying to find. I'm trying to find d dx of f inverse of 3 and d dx of f inverse of x evaluated at 3. What is the difference between those two questions? Oh, there is definitely a difference. Has to do with the order. What is f inverse of 3? Ignore the d dx. What does f inverse of 3 mean? What's that? What? No.
Oh, no, that's extra. So it's the inverse of f.
Yeah. Yes. So this one, f inverse of 3 says, find f inverse and plug 3 in, right? And take the derivative of it. So if you ignore the d dx, right? If you had some formula for f or f inverse of 3 would just mean, okay, plug a 3 in there, right? And what do you get when you plug a 3 into a function? A number, just some number. Yes. So this is just some number, right? F inverse of 3 is just some number. So what you get when you plug 3 into the inverse function f. What's the derivative of some number? 0. So this first one is easy, right? d dx of f inverse of 3 is 0. Because they're asking you to take the derivative of a constant. F inverse of 3 is just a number. It's the number you get when you plug 3 into the inverse function. So that one's 0. This one is asking you to take the derivative of f inverse, then plug in 3. So this one we have to take a derivative, then plug 3 in. All right, so the derivative of f inverse, we have a little formula for it up here. It is f prime evaluated at f inverse. So write it down here, d dx of f inverse of x is 1 over f prime evaluated at f inverse of x. So if I were to plug a 3 in there, I'll just put evaluated at x equals 3, evaluated at x equals 3. That's 1 over f prime evaluated at f inverse of 3. Okay, now look at the table of values they gave us. What is f inverse of 3? 1/3. So I need to do 1 over f prime of 1/3. What's f prime of 1/3? -5. So this is -1/5. Does that make sense? Just plug it into the formula. Okay, so moving on to your classwork for the day, derivatives and inverse functions. You are going to start by trying to find a formula for the derivative of log base 10 of x. So we know ln x. Now you're going to work on finding a formula for log x, and I've given you a little hint on how to get it.